We said that we are using two software mainly, CAD software for obviously designing our parts and CAM software for preparing our design file for manufacturing. And in between, we need to convert our file to an STL file, submit it to the CAM software, as you know. And the most popular one is STL. We said that there are problems with the STL. You cannot have color information, material information about, or any interior structure information cannot be stored in STL files. And we may have binary ASCII versions. And another issue, we don't have any dimensions, so it might be millimeters, centimeters, or even meters. We don't store any dimension information. We make use of triangles. Their vertices and normal vectors are required. And we need to have some numbers for each triangle, as you know. But these days, some people are working on different file formats to overcome the disadvantage of STL files. But the advantage of STL files is that it's a very simple format. You can, for simple shapes, you can even write with your hands. You don't need to use a CAD tool. Another advantage, it can be, let's say, imported into any CAD software. It's a very common format. It's not standard, but it's a de facto standard. We discussed the details. You already know it. So you need to define the triangles in this STL format. As you know, the normals should be given first, and then the vertices of the corresponding triangle. And we know that the normals should be unit normal vectors. And we need to have some bias reserved for specific parts of the file. Obviously, the largest to the region is reserved for the values of the triangles. We simply create it by saving your model in STL file format. It's not that complicated. If you have high number of triangles, then the approximation will be very good. You will have less approximation, geometric errors, but if you use less number of triangles, then it will be a worse approximation and you will have some errors. And as you know, in the CAM software, after you import this STL models, STL things in your table, then you need to do slicing, since it's an additive manufacturing or layer-based manufacturing. We need to do slicing, and this is the most difficult part of, most complicated part of CAM software. After they have the geometric shape on their table, by using the available settings, they need to obtain the contours first, and then fill the interior of each slice, and then represent them as G-code files, and these G-code files will be utilized on the machines. So what we are going to do, we will be using two main algorithms. The first one is for obtaining the intersecting lines. If this is one of the edges of the triangle, and if that's the slicing plane, we need to obtain the intersecting portion of that triangle with the slicing plane. And then later what we are going to do, we will simply orient these lines so that they are connected and we have a close contour on that slicing plane. Any questions, guys, up to now? Since I will start going into details of these algorithms, and it might be a bit complicated than the previous slides. If you have questions, feel free to ask now. Okay, this is the first one. If you remember, we discussed this one on Thursday. This is for testing all the triangles with the slicing plane, whether they have intersection or not. So what are we doing? We simply read the STL file, get the facet information or triangle information from the STL file, and do some operations on all these triangles. So what we do, we get the vertices of the triangles, we check the vertices of these triangles, whether they have intersection. Why it's not working? Sorry. Yes, pen. So assume that this is a triangle, and if you have such a slicing plane, obviously we don't have any intersection, but once you have an intersection like this one, then you need to compute these intersection points and obtain this line segment, this intersecting line segment. So this is done here. If there is no intersection with that triangle, then you should continue with the next triangle in your file. But if you do have an intersection, then what do? You then need to store this intersecting line. This intersecting lines should be stored into a kind of a list. And in that list, you may have 2 columns maybe. One for starting point, another one for the stopping point or end point, okay? So the coordinates of these points should be stored. And once you are done with all the faces, all the triangles, then you are done with this algorithm and you can switch to the next algorithm, which is about ordering these line segments. Since in this list, we will have these, let's say, lines in a random manner. They are not ordered. We don't have a contour. We don't have a closed contour. They are irregular. So in the next algorithm, we need to obtain a connected order or connected profile. So there's a question. The slicing is performed on the CAM software. So if you consider that CAM software is the part of the machine, so the question of your friend is that I'm sorry, since he's just sent a direct message, please ask your questions in the general chat area, not as a direct message. Is the slicing performed in the AM machine? The question is like that. The slicing performed whether on the machine or not. If you consider the CAM software as a part of the machine, then we can say that yes, the slicing is performed on the machine. But if you consider the software as a separate item, separate part, then we cannot say that the slicing is performed on the machine. It's performed right on the CAM software, not on the machine. And I prefer to say that the slicing is not performed on the machine, but it's performed on the CAM software. Another questions, guys, about this first algorithm, the algorithm we are using to obtain this intersecting portions. Yes. So for the intersection, we have 5, if you remember, 5 scenarios. Some of them are simple. Some the 5th one is a bit complicated. I think, as far as I remember, we spent maybe about 15 minutes on the discussion of these cases. The first one is, as you see, all the vertices of a triangle lie above or below the intersecting plane. So it is the simplest one. If this is a triangle, then our slicing plane is above or below the triangle. So that means the triangle will not be contributing to the profile, so we can simply skip it and don't spend time on it. But for the rest, it's a bit different. And for the last one, we need to spend more time on the last one, since we need to do some computations for the intersection of your lines with the plane. So let's have a look at the second one once again. A single vertex direct lines on the plane, which means that if that's the slicing plane, we have just a single vertex on this plane. And again, you can simply ignore it, since if that's the case, then probably some other triangles are also the neighbors of this triangle should be intersecting with the same, let's say, triangle. So we can say that this point, the point of this first triangle, which has a single connection with the plane, will be included in the intersection of the other triangles. So you don't need to focus on that triangle. You can again simply ignore it. Then if you look at the third one, two vertices lie on the plane. This is a very simple case. So then what we are going to do, let's make it longer, the slicing plane. In the third case, one of the edges of our triangle is directly on the slicing plane. So what we do, instead of doing some computation like in the case of the fifth one, we can simply store this as a starting point into our, let's say, list of line segments, and this point as the end point into our, once again, list. So without any computation, you can directly store these vertices into your list of line segments. Okay?
Hocam bir şey sorabilir miyim?
Sure.
Bu triangle'ın diğer köşesine ne oluyor? Onu eliyor muyuz?
Do you mean this one?
Evet.
But our focus is this value. Let's say z is equal to some, I'm making up, let's say z is equal to 10. Probably since we are going from bottom to top, we have already processed it. So we don't need to focus on that vertex. Or this parts, this interior regions are already being processed. We don't need to worry about the remainder of the triangle. Our main focus will be on this part. Okay?
Tamam hocam, sağ olun.
Any other questions, guys, on this on this part of this first algorithm? So this is another question. When the topmost surface is composed of only one vertex, is the second scenario what we store it, right? It's a very specific case, but you mean, I think we have a kind of a pyramid, right? Is that what you are discussing? So we may have such a pyramid or a tetrahedron, let's say. It's a very specific case. If that's the one, yes, you can say that you don't need to store it actually, the top one. Why is that? Can anyone tell me if you just have a single point left at the top? So if you look at the top view, that will be the intersection, a single point. Do we need to store it?
Hocam
It is already stored in.
Aynen.
I couldn't get your point, so you say that it's already stored? No, it's not already stored, and it's not processed yet.
It is stored in a different triangle.
No. We don't need to store it actually, since our printer cannot print a point, obviously, a single point. That will be highly difficult, and at least we need to have, maybe I'm drawing it from the front view. It's better we stop it somewhere here. Since having a sharp corner is not possible in additive manufacturing. We will always have kind of a radius there. It's not possible even in that type of additive manufacturing or stereotypography. It will be quite difficult. We will not have a very sharp point there due to the nature of our, let's say, additive manufacturing.
Hocam ben şey diyecektim. Zaten bu noktanın bittiği yerden direkt başka bir üçgen çıkmayacak mı zaten? Onda store olmaz mı?
But your friend is saying that you have a pyramid to be printed. This is your final shape.
Okay. Tamam, şimdi anladım.
Okay. So any other questions, guys? Yes, I think we are done with the third case. Now let's have a look at the fourth one. So this was a bit complicated, if you remember, so I need to clear my screen. This is okay. Now we will be working on the fourth one. So in the fourth one, we have two cases. The first case is a bit very rare case. So in all the, let's say I will be focusing on 4.1 first. In 4.1, we are saying that the whole triangle will be contributing to the profile wholly. And if you remember, this is the main thing about the fourth case. The three vertices are lying on the plane. So we can say that we have a kind of an tetrahedron. This is a tetrahedron, guys, and this is top surface, okay? And my slicing plane is exactly at this level. So if I draw it on the front view, that will be my slicing plane. And that's the intersecting part, right? Since the triangle is just, we have a single triangle at the top surface and it's coinciding with the slicing plane. So I can simply say that the contour is the triangle itself. So if you draw the top view, that will be the contour actually we are looking for that plane. For that corresponding plane, that is the contour we are looking for, and we don't need to do any further processing. So you can simply skip the second algorithm since we don't need to order them. We have the triangle already ordered. That will be our order in counterclockwise. First, second, and the third edges. So that is all for that specific plane. But as I said, this is a very rare case. Maybe just for 1 out of 1 million cases, you will have this scenario. But let's have a look at 4.2. This is more common than 4.1. And let me draw the first top view. Assume that this is the contour of the top surface. Again, our vertices are lying on the plane. This is again the top plane, but this time we may have some triangles interior. So that might be the triangles. And as you see, some triangles, for instance, here, they just have connection with the other triangles. They don't have any connection with the boundary. So the thing is that if that's the case, we can simply ignore them. These interior triangles can be ignored, and we can work on the triangles having connections with the boundary. And the rest is not that difficult. We can use the previous rules. There maybe complete edges might be contributing to the profile, like in this case, the third scenario here, or they may be connecting to the boundary from just a single point. And you can simply ignore it. So you may be using just the second or the third cases for 4.2. And the thing is that at the beginning of 4.2, you need to ignore the triangles inside this region which have no connection to the boundary. Any questions, guys, about the fourth case?
Hocam kontürün üstünde olan üçgenlerin içerideki köşelerini de ignore mu ediyoruz?
Yep.
Tamam.
They are not contributing to the outer boundary.
Teşekkür ederim.
You're welcome.
Hocam o zaman boundary'e sadece bir köşesiyle dokunan üçgenler için onları neden katıyoruz? Diğer yanındaki üçgen zaten o dokunan köşeyi de boundary'sinde olmayacak mı? Yani ortak olmayacak mı?
Right. We can also ignore, according to our rule 2 or case 2, we are also ignoring these. But we cannot ignore this one and the other one here. Or it's an approximation. You may have another line here. You cannot ignore these. You should store the edges of these triangles, and they are actually the third scenario here. You're right. Now let's focus on the fifth one. Not that complicated. In this case, we have a kind of a triangle once again, and this time we have an intersection with the slicing plane. And we need to determine these intersecting points and then store them into our list so that later we will order these portions to obtain the outer boundary. So this is how we do how we calculate the intersections. We do a kind of a projection first on the y is equal to 0 plane, so that the values of the x values of the intersection will be determined, since the z values are already known, since zi is the height of our slicing plane or intersection plane. Okay, we don't need to do further processing for zi, but this is the single unknown here. These are already known, since these two are the vertices of the triangle. We don't need to do any computation, they are already known. So by doing a kind of an interpolation, we need to determine xi. And once we do it for y is equal to 0 plane, we need to repeat it for x is equal to 0 plane to determine yi. And then later, with the help of these, you will be done with the first intersecting point. So you have determined the first intersecting point, since let me switch to the pen once again. So if that's it, we have 2 points, and now just a single one is computed here, and we need to do it for the second edge so that the intersecting line segment will be determined. Any questions, guys, about this intersection issue? Okay. So there's a second algorithm. After you obtain the intersecting portions, then what we are going to do, we need to order them, and after this ordering, we'll obtain a proper, let's say, contour. So if that's your contour, then in this algorithm, we will have these random portions. They're not ordered initially. Let's say this might be the first one, this might be the second one in the list, this might be the fourth. So we will do an ordering, and at the end of this ordering, we will have such a closed contour. So let's have a look at the details of it. The input to our algorithm is a kind of a list. So we start with a list of line segments, and in this list, we need to have start and end points, and the coordinates of all these points should be given. Okay. We will start with such a list. So this is the line segments. And we will have n of these line segments. And after these, at the end of it, the output will be the ordered line segment. This, for instance, you may have 8th one, the first, and then let's say 5th one, 3rd one, maybe the first one, then 7th one, 9th one. So that will be the output of this algorithm. It will give you an ordered list of line segments. So how we are doing it? We simply select a line from the input line segment list. Probably we are going to get the first one, and then what we do, we simply store it into the new line matrix. And then what we do, we check the tail and the head of this line segment. We know the end point, we know the starting point, So this is a kind of an arrow, and it has a tail and a head. And what we do, we check the distance of this tail with all the line segments. We have many line segments in our list, so we check the distances to all these line segments. Check the distance to all the tails, all the heads, and try to find the minimum one. And it should be, if it's a single, let's say, closed loop, you should find a line segment having zero gap between the tail of this line segment and the start or the end point of another line segment. After you find it, then according to whether this zero distance is between the tail and the tail of another, let's say, line segment, then what we do, if you have the minimum distance or zero distance between this one and the one we are actually working on, then we need to do some kind of reversing operation so that the tail of this one will be connecting to the head of the new line segment. So we need to do some swapping operation. But if you find that the tail has a distance between the head of this new line has a zero distance between the tail of the initial line, then you don't need to do any swapping. You can simply keep it as it is and store it into your ordered line segment. So that will be your output list. And again, you should be storing the line segments this time. This should be ordered. Okay. This algorithm, this flow chart is actually summarizing it. So as you see here, after you got a line, then you check the distance of this line with all the other lines, find the minimum line, minimum distance. And then what you do, if this minimum distance is related to the head of the line, then you do kind of an storing. But if that's not the case, you need to do swapping operation and then later store it. After you process all these lines, then you'll be done with this algorithm and output this ordered list of line segments. And that will be giving us the kind of polygon. This countered polygon will be output, and you will obtain the final boundary and switch to the third algorithm. Before jumping to the third algorithm, do you have questions, guys? Okay, no questions. Good. So that's the third algorithm. In here, what we are doing, we are trying to fill the interior. So we are kind of a contour. And in this algorithm, actually, we are filling this interior in such manners. So this is how we are doing in this algorithm. So this is the filling algorithm, the third algorithm we are discussing now. The first one was obtaining the intersecting lines, and the second one was ordering these intersecting lines, and the third one, the last one, is about filling the interior. Since in additive manufacturing, we need to cover the interior so that the parts will be stronger and we will have material inside the object. So this is actually the summary of the flow chart, what is going on here, but let me do it one by one. So we are starting from the origin, and let's assume that this is our building plane, this is our origin, X and Y, okay? This is 0, 0. So what we do, we set the plotting system off. So this means that it is an extrusion-based process. We are extruding nothing, and we are just starting movement in X direction. So after turning the system off, what we do, we increment scanning in X direction. So this is how I move in that step. Since my X is 0 initially, so I move in X direction. And assume that this is our boundary. We cannot go beyond. Increment scan in X direction, contact with the profile. Assume that I have a kind of a profile here. No, I haven't contacted with the profile. Is X max reached? Yes, I'm now at, this is X max. And this point is Y max. Did I reach X max? Yes. Then what I do, I check whether I reached Y max. What is the answer to that question? No, I didn't reach Y max. So what I do, I make my X is equal to 0, but increment Y. So I go to X equal to 0, and but Y is incremented. Assume that this is here. So I do one more pass. But again, I will have no contact, and I need to once again go back and increment Y. Assume that right now I am here. This time, when I come here and I touch this profile, did I contact with profile? Yes. So what I do, I change the plotter state, which means that I need to turn on my extruder, or I need to turn on my laser and start some maybe fabrication. So after I turn on my plotter, what I do, let me use a different color for the plotting on case. So what I do, I continue going in the X direction. So I go in this direction, and then later I contact with the profile. Yes. Then what I do, I change my state. Let's change the state here. Oops. I should make it red. Yes. And I continue moving in X direction. And now I didn't contact it with the profile, but X max has been reached. Yes. And Y max hasn't been reached. So I need to do one more operation. And if you follow this flow chart, you can finish this interior filling operation. Any questions, guys?
Can we define the interior texture in this stage?
Sure, but in the simple, let's say, flow chart, we just have linear interior patterns. For other ones, you need to have some extra, let's say, blocks here, so that you may have a kind of a zigzag instead of just an single lines. Since if you have a kind of a zigzag here, you would gain time. Oh, let me draw it here. If you do it such a way, you will be losing less time, and in a shorter time you can do the filling operation. But this is what this algorithm is doing, not this one. This is zigzag, and you need to have some extra comments here. Might be a nice question. What type of blocks should we add to make it zigzag? So can everyone tell me what we need to do if you want to do it a kind of a zigzag instead of straight lines?
Maybe in the second contact, increase the I increment.
Might be instead of equating X to 0 here, we may keep it X as it is and do the scanning in the reverse direction. And maybe we may be doing scanning in minus X direction. Yep, Çağatay, this is what we have discussed, similar to your answer. Thank you. Any questions, guys, about these algorithms? We have seen 3 of them: finding the intersecting portions, ordering them on the layer, and then filling the interior of these boundaries.